So again, my name is Shankar. I'm the technical director for ActiveIQ. And we've built a pretty interesting hybrid cloud architecture that powers all of ActiveIQ. Right? This is the portion that we call the brain of ActiveIQ. And so we get these 300,000 storage endpoints sending 200 billion data points a day, or 10 trillion data points a month. And we have to do something with it. We have to provide insights for our customers. So all of this feeds a massive data lake, right, including some other infrastructure to derive insights. And then ultimately it's visible to customers either through a desktop application, mobile application, or APIs, right? One of these three things. So we've had Hadoop in our ecosystem since roughly 2012. Before 2012, it was just a database, and that didn't scale. So we transitioned to traditional Hadoop in 2012, and we've done a bunch of things that I'm going to describe. One of the things we very quickly ran into is the scale at which we were growing, right? Actually, soon after we deployed Hadoop in 2012, just a couple of years later, we were quickly running out of space. And deleting your telemetry data is not a good answer, because that's actually useful information. So we have built something that has produced a lot of benefits for us. I'm going to start with the benefits and then get into the architecture. So we have seen a 30% reduction in operating costs, makes the bosses happy. A massive reduction in the storage space we need, even though we're accumulating more data, right? A 12x reduction in space. 3x fewer compute nodes. And also we have had a massive reduction in the time it takes to create a new API or a new service. Let's say we build a new predictive service. Our goal is to get this in front of the customer as soon as possible, right? And today we can turn this around in many cases in literally a week. So we'll start with this on-premises architecture. This is, again, a 50,000-foot view of what many people have on-premises for Hadoop and AI. And it consists of 4 parts. The first part is the acquisition of data. Right? So typically, you have some incoming telemetry data. In our case, it's the auto-support messages, the telemetry from the different storage controllers that lands in a piece of software called Kafka. All that is a distributed log. Okay? Very commonly used, and people use some other things around it as well. So that's as far as the acquisition of the telemetry data itself. Once you've acquired it, you've got to now clean it. You've got to clean it, you've got to curate it, you've got to process it. Very often, this telemetry data is unstructured. It's got a lot of data integrity issues with it. And people, again, traditionally use Hadoop to do this. When I say Hadoop, it's a broad term. I mean both the traditional Hadoop as well as Spark. So we actually have 2 Hadoop clusters that do these things. One is a real-time cluster that acts on telemetry data the moment it arrives and does some things with it. So remember I said that if we get a failure message, we have to respond to that in under 2 minutes. So that operates in our real-time cluster. In addition, we keep historical information around in our data lake where we can go back and look at trends over time, right? And now you might ask, why are these 2 separate things? Why aren't they just one cluster? Well, it turns out that Hadoop's really not very good about isolating workloads, especially from an I/O perspective. So people do end up having multiple clusters. Then what we do is we take all of this cleansed and curated data, structure it, and put it in a NoSQL data store. And all our machine learning work and AI work runs off this structured data in the NoSQL stores, right?
Sorry, isn't that an oxymoron?
Oh, you mean the NoSQL and the...
Yeah, I'm mostly teasing, but I'm just going to ask more. So
yeah.
What does that mean?
Well, so it means that, so again, NoSQL is a very broad term for, right?
Yeah.
It could be SQL as well. But you have to fundamentally structure the data before you can do anything useful.
That's right.
Right.
Thank you.
Yeah.
I'll ask you more questions later.
Sure. So that's what feeds our machine learning models, right? That's the third part of this pipeline. And then the last part is serving up the results. So that includes building APIs that scale our UI and things of that sort. Okay. Now I'm going to talk about 3 challenges we had with this architecture. And by the way, I've spoken to, in the last 6 months, I've spoken to more than 100 customers that ironically enough come to us with the exact same problems that we've run into, right? So the first one is the data management challenges with traditional Hadoop. The traditional Hadoop architecture, most of you probably know, is just software running on these direct attached servers, right? So you have a server with some cheap disks attached to it, and you just scale horizontally. And the way you get performance and availability, or rather durability, is by making 3 copies of the data. Right? Now, of course, this has changed in the new versions of Hadoop. The new versions of Hadoop have something called erasure coding. And that cuts down so you can get away with sort of half the space. But it has other consequences, so it's not ideal. Right? So this is traditional Hadoop, 3 copies of the data. But what does this mean? It means for a lot of customers that you have very poor utilization of compute as you keep growing the data. See, I think there's 3 categories of people doing big data, right? There's the companies that have these Hadoop clusters with 20,000 compute nodes or 50,000 compute nodes, because they really need all that compute power. And for them, this architecture actually makes sense, because they need all that parallel bandwidth that they can get across so many nodes. But you can count them on your fingers. They're hardly, there's not very many of those. Then you have the customers that are really tiny, right? They probably should just be using a database, right? But what you have now is this massive segment of enterprise customers that are somewhere in between. They're getting vast amounts of telemetry data. They need to store all of that, but they don't need to process all of that all the time. There's a hot amount of data that they're processing maybe per week or per month. And so this architecture actually doesn't work well for them, because they end up with a lot of unused compute. And it's a misnomer that Hadoop is free, because you go to most enterprise companies, right? Hadoop is open source, but nobody just runs open source, right? You actually pay someone to maintain all of that. So you have no license cost that you have to think about. The second thing that happens is, like I was saying, because Hadoop's not very good about managing, isolating I/O, you end up creating different environments, perhaps one for QA, one for batch processing, and so on. And you end up copying the same data across all these clusters. So you end up with lots of copies of the data. And the last piece is it's not very good at tiering or remote replication of the data. So we ran into these challenges. The second set of challenges we ran into have to do with data science. So we hired a bunch of data scientists a couple of years ago. And then the first thing we learned is they all had different favorite tools, different favorite libraries, and they all wanted to use the cloud, right? They wanted nothing to do with IT. Right? And so we had this problem where they would take the cleansed data and copy it to their favorite cloud, and we discover this later. And by the way, this is a story that repeats at every enterprise customer I've spoken with, right? They have their data scientists just trying to copy data off to their favorite cloud, and then that becomes a risk. So we had to shut that down really fast, yet give them the flexibility of using the cloud, right? And in the middle, we have the data engineers. These are the people that are actually transforming the data, and they need access to a lot of compute and high-performance storage. So how do we meet the needs of all these people, and especially when they have conflicting needs, right? A lot of conflict between the IT architects and the data scientists. The last challenge has to do with the speed of deployment. See, in this business of trying to derive insights from data, your advantage really is how fast you can take an idea and transform it into an insight for the customer, right? And so you have to deploy these pipelines. When I say pipeline, I mean all the way from ingesting the data, transforming it, doing machine learning. All of this you have to deploy into production really fast. And if you're completely on premises, it turns out you can't do that very effectively, okay? Because these different parts of the pipeline, ingesting, cleansing, the AI, they use different pieces of hardware and software. And upgrading all of that and maintaining that is very time consuming. But the good thing about it is it's very secure. It's in your data center, right? You have complete control over that. And you also have a complete understanding of the costs, because you typically buy some infrastructure over a 3-year period, and that's how much you pay. If you go to the cloud, on the other hand, you get the speed of deployment, right? You can programmatically deploy these pipelines blindingly fast, but then data security is a huge concern, and you really don't have a good understanding of cost. We've seen these situations where, 1 month you're spending very little, and then the next month it's going out of control. So how do you get a handle on this? So what we decided to do is take a hybrid approach. So we said any analytics, anything that is real-time in nature, or that's very compute intensive and where we understand the bounds of that compute, that stays on premises, okay? Because we can control the cost that way. And we also get the performance that we need. The second thing we did is we built a unified data lake. I'm going to talk about that in the next slide, actually. That consolidates all these different data silos for different reasons onto a single storage system, okay? And so that saves space, cuts cost, and so on. And to give our data scientists the flexibility they need, we let them use any cloud that they want, but they do this by working with cloud-connected storage. So what do I mean by cloud-connected storage? So NetApp really has 2 forms of cloud-connected storage. One is what we call NetApp private storage. So that's just a NetApp box that you buy, and you deploy it in a colo, like, for example, Equinix. And that's physically co-located with cloud endpoints. So you have a very low latency link to Amazon or Azure or Google. The second option is the new NetApp Cloud Volume Service, right? So there, it's a slightly different model. You're essentially, clicking a button and you get some space, right? It's pay as you go. So you can use one of these 2 techniques to essentially get secure cloud-connected storage and tap into any cloud that you want. Now, if you use NetApp private storage, which is a box that you buy and maintain, then you can technically connect to that storage device from multiple clouds at the same time. And in fact, we do that today, right? We have data scientists that are using Amazon and Azure simultaneously on the same piece of storage.
Are you using the same volumes in any case, like where they're connected to the same?
Yeah.
So it's one instance of storage and both clouds connect?
Yeah, we actually have people doing that. Yeah. And we use, we loosely call this the data fabric, but we have multiple efficient mechanisms of transferring data from on-premises to the cloud, right? So many of you are probably familiar with SnapMirror, and then there's something called Cloud Sync. So depending on what you're using for cloud-connected storage, there's different mechanisms you can use that automate the movement of data. Okay, so this is what our unified data lake looks like. What we've done is we've taken our Kafka ecosystem, our Spark ecosystem, and even I think there was a tech field day on ONTAP AI. You can take all of these things and now point it at the same storage box, right? So we've taken all the stuff that used to live in HDFS on DAS and put it on an NFS controller. Actually, to be more specific, an all-flash array, right? And you might wonder why would we do that, right? That seems like a strange thing to do. But the first thing we saw right away is a massive reduction in the space we were using. So we don't have to make 3 copies of the data anymore, because ONTAP's highly available and it's got RAID, DP, or TP underneath. We get the same durability as the traditional Hadoop file system. In addition, NFS is visible to all the compute nodes, right? And we can turn on all our space-saving features like deduplication, compression, compaction, all of that, right? So we get really remarkable reduction in space due to compression and compaction. I have to point out that it's the nature of our data that allows that. So if it's like performance counters and logs, those compress very well. But if all you had were a bunch of videos and images, that won't work here. So with all of that together, we get between 12 and 14x space reduction compared to the original Hadoop HDFS. Then what we do is we have our storage grid, which is our low-cost object store underneath. We keep 1 copy on the west coast of the US, 1 on the east coast. And we can automatically tier cold data off from our all-flash array into storage grid. We can do that today using this thing called fabric pools, right? Which I think probably many of you know about. The nice thing about fabric pools is, actually two nice things. One is it's automatic, and the second thing is it preserves all the storage efficiency that you've got on the primary storage system, right? So you end up saving a lot of space in the archive tier as well. And the last part is, well, how do you connect Hadoop to NFS? So there's two parts to this answer. If you're running only Spark as we do, it doesn't really matter because Spark is storage agnostic, and you can access NFS directly, no problem. But if you do happen to have more traditional Hadoop jobs, for example, using the MapReduce paradigm, which is tied at the hip with HDFS, then you need a way to do that. So what we've done is we've built a piece of software that we give away for free. It's called the In-Place Analytics module, or as I like to call it, the NFS connector. And it's just a Java library that you drop into all your Hadoop compute nodes, and it makes our NFS look like HDFS. Now, this has been certified by one of the big Hadoop vendors, and we have tested it pretty extensively, right? So that's an option you have. So this is our unified data lake, okay? And because it's flash and we manage our caches very effectively, we've actually got up to a 30x performance increase for our entire data pipeline. Something we did pretty recently is we added, in this unified data lake, we created what we call a flex group. So a flex group is a feature in ONTAP that makes a bunch of disks look like a single namespace, right? It's a namespace that can grow very large. It can have 400 billion files and 20 petabytes of space underneath. So this is really nice because we were adding about 250 million files a week into this ecosystem, right? So we were constantly going to IT and saying, create a new volume for me, create a new volume for me. We don't have to do that anymore, right? In addition, because flex groups balance the load across a cluster, a bunch of storage controllers, we've actually had a 20% reduction in the running time of our jobs. So it's been a pretty nice side effect. Okay, so that's as far as on-premises go, right? The left side of this picture. We also had to handle the cloud part of it, right? Which we do, like I said, using NetApp private storage or the new Cloud Volume Service. We have built, honestly, very extensive infrastructure using Amazon, but we do have people using Azure and Google as well, including a team that uses IBM. So we're truly multi-cloud for this ecosystem. But what we've done is we've built an ecosystem that lets us serve up results or build a new service blindingly fast. So today, let's say you want to make a new prediction. Let's say we didn't have capacity forecast. Let me take something really simple, right? And so you had to build this little widget in ActiveIQ. Today, you can do this really fast using this hybrid cloud architecture and using some templates that we have in Amazon along with our cloud-connected storage. You can provision this and have it show up in ActiveIQ in under a week, right? The second thing we've done is we've ripped out our on-premises Hadoop QA cluster. See, because here's the thing about QA. You're not doing it all the time, right? You're doing it once in a while, so why have a physical cluster for that? Again, using the power of the cloud with this cloud-connected storage, we can spin up our QA clusters programmatically, have them run all the tests and shut down automatically, right? So that's led to a cost savings as well. So this is a final summary of some of the advantages we've seen. One thing that I don't have in my slides, but we're actually very close to doing, is taking this whole data pipeline and making it a Kubernetes service. Right? So Spark support for Kubernetes, hasn't been the best as far as the vendors go, but it's getting there, right? And we've done a bunch of things ourselves. So we're at a point where a developer in our ecosystem can literally, with changing a config variable, have these pipelines run at will on any cloud that we choose or on premises. So that's what we have.
I'd love to see that demoed.
Sure, yeah, why not? Yeah. And this has turned out to become a very powerful reference for our customers. So, like I said, I've personally spoken to more than 100 in the last 6 months. All kinds of workloads, people, very large number of connected car companies, people building self-driving cars, all that stuff, defense, healthcare, all over the board. And they have the exact same problems that we have had, right? They all want to produce insights rapidly, very low cost. It's the same sort of problems.